In the last lecture, we were examining the oscillatory flow in a pipe due to a sinusoidal variation in the pressure difference across the ends of the pipe. So, this is an unsteady because the pressure difference is oscillating in time, but fully developed that is there is no variation in the streamwise direction. Okay. There is a pressure gradient in the streamwise direction, but there is no variation in velocity in the streamwise direction. Okay. And the pressure gradient we had taken as partial p by partial x is equal to k times cos of omega t. And if you recall, the equation was for the momentum balance equation, rho partial v x by partial t is equal to minus partial p by partial x plus mu by r. Yes. Okay. Where this pressure gradient was of an oscillatory form. Here the pressure gradient was of an oscillatory form, a cos function. Okay. And we had defined the scales, okay. R star is equal to r by r, okay. T star is equal to omega t, if you recall. And the velocity could be scaled either by the viscous scales or the inertial scales. Okay. The velocity could be scaled either by the viscous scales or the inertial scales. You would use inertial scales when inertia is dominant and viscous scales when viscous effects are dominant. That will come from the dimensionless number, that is the ratio of inertia and viscosity for this particular case, which in the last lecture we had obtained Re omega. Okay, a Reynolds number based upon the frequency and the pipe radius, okay, where the radius is r. Okay. So, you can scale it by either the viscous scales or the inertial scales. If you recall, what we had done was to divide this entire equation by k. Okay. We had divided this entire equation by k. Okay. We divided this entire equation by k. And then this forcing function is dimensionless, cos omega t is dimensionless, and therefore, all other quantities are dimensionless, and that gave us two scales for the velocity. Okay. I am sorry, this should be capital R. Should be smaller. Okay. And we had chosen to scale it by the viscous scale. Okay. And I had said that we will come back later and see what happens if inertia is dominant. So, the velocity scaled by the viscous scale is going to be equal to Vx mu by k r square. Okay, that was the viscous scale that we had selected in the last lecture. And if you do it this way, the equation becomes Re omega partial V x star partial t. Subject to boundary conditions, the velocity is equal, let me write it right. Okay. Velocity is 0 at the wall of the pipe, and the velocity gradient or the derivative of the velocity with respect to r is 0 at the axis. If you recall, in the last lecture we had, instead of solving this equation, we had framed an alternate equation, okay, which is a more general a generalization of the equation that we had, okay, that is partial V x plus by partial t. Is equal to minus e power I t plus 1 by r d by dr of r partial V x plus by partial r. That was the more general equation that we had formulated in the last class. Okay. The forcing function for the original problem, okay, is the real part of the forcing function of this more general equation. Okay. The solution for this more general equation is a complex function. V x plus is a complex number, okay, where I is equal to square root of minus 1. Okay. And e power I t is cos t plus I sin t. Okay. So, the real part of that is cos t, which is the forcing function for the original problem. Therefore, the solution of the original problem is going to be the real part of the complex function V x plus. Okay. So, I can get the solution by just writing V x star is equal to the real part of V x plus. And in this equation for V x plus, the inhomogeneous term is an exponential. Okay, the inhomogeneous term is an exponential, and the equation is a linear equation in V x plus. Therefore, I could use the substitution V x plus is equal to V tilde, okay, of r times e power I t. Okay. Okay. And then the equation becomes I r e omega into V tilde, okay, is equal to minus 1 plus 1 by r. Okay. This is now a total derivative. Now, this V tilde, the function that I have here, is only a function of r, and all of the time dependence comes in through this e power I t. So, if I make this substitution into the equation for V x plus and then divide throughout by e power I t, I will get this ordinary differential equation. Okay. And this ordinary differential equation has boundary conditions. The velocity is equal to 0, okay, V tilde of r is equal to 0 at r star is equal to 1, and d V tilde is equal to 0 at r star is equal to 0. Okay, so, those are the equations and the boundary conditions that have to be used for solving this equation. So, once I get V tilde, then from that I substitute here and we get V x plus, take the real part of that and get V x star. Okay, so, how do we solve this equation? Okay, take the inhomogeneous term to the right side and all the dependence of V x on the left side. Okay, so, if I do that, I will get 1 by r d by dr of r partial V x partial V tilde by partial r, okay, minus I r e omega V tilde is equal to 1. Okay, that is going to be the equation. Okay. So, expand out. Okay. So, I can expand this out to get d square V tilde by d r star square into 1 by r square plus 1 by r d V tilde by dr minus I r e omega V tilde is equal to 1. Okay. And this equation will have, it is an inhomogeneous equation. So, there are two parts of the solution. This okay, of R, it consists of a general solution or a homogeneous solution, let me call it as a homogeneous solution, plus a particular solution. Okay. The homogeneous solution is the solution that satisfies the homogeneous equation with the inhomogeneous term on the right side set equal to 0. Okay. The homogeneous solution satisfies the homogeneous equation with the right side equal to 0. Second order differential equation, it will contain two constants. The particular solution is any one solution of the equation. Okay. Any one solution. Okay. You can find the simplest solution as the particular solution. In this particular case, the simplest possible solution for the particular solution is just a constant, because if you assume that this V p is a constant, then the first and second terms on the left side turn out to be equal to 0 because they are derivatives. Okay. And therefore, any constant that satisfies this equation can be a particular solution. In particular, if I say that V tilde is equal to minus 1 by I r e omega. Okay. This is the particular solution. Okay. This satisfies the equation. Okay. So, it can be chosen as a particular solution. I can also write this as I by r e omega, because we know that I square is equal to minus 1. Okay. Okay, so, if I multiply this by I square, okay, I will just get minus of I by r omega. Okay. So, this particular solution, which is a constant, satisfies the governing equation. So, it is a valid particular solution. The constants of integration will all come in from the homogeneous part of the solution. Okay. The homogeneous part of the solution satisfies the equation 1 by r square, sorry, I am sorry. Okay, so, I should kindly note this change. This is d square v by dr square plus 1 by r dv by dr. Okay, it's when you expand out this derivative, there is no 1 over r square there. It's just d square v by dr square plus 1 by r times dv by dr. Okay, so what I can do is to multiply. So, the equation for the homogeneous part is going to be Okay, that is the equation for the homogeneous part with the inhomogeneous term on the right side set equal to 0. Okay. And I can multiply throughout by r square to get it of a more familiar form. So, I multiply the entire equation by r square and I will get on the first term here, I will get r square. The second term will just be proportional to r and the constant has a r square in it. Okay. Now, you can easily verify that the first two terms have 0 net dimension in r. So, if I multiply r by a constant, the first two terms do not change. Okay. It is only the third term that changes. Okay. So, therefore, I can define r star is equal to square root of minus I r e omega. Okay. I am sorry, r plus is equal to. Okay. And if I do this redefinition, then the first two terms on the left do not change because they have 0 net dimension in r. So, I will get r plus square d square v homogeneous by dr plus square plus r plus okay, minus I r omega r star square is equal to r plus square from this equation. Okay. So, this gives me plus r plus square times v homogeneous equal to 0. Okay. So, this is the equation expressed in terms of this r plus, which is square root of minus I r e omega times r star. Okay. And we have seen this equation before. If you recall, when we solved for heat conduction in a cylinder, the equation we got was r plus square d square T by dr plus square plus r plus square minus n square T. Okay. So, this is the same equation as that equation with n is equal to 0. Okay. This is the same equation as that equation with n is equal to 0. Okay. Which means that the solutions are the same as the solutions for that equation with n is equal to 0. Okay. So, the solutions for the homogeneous part are A j naught of r plus B y naught of r plus. Okay. A j naught of root of minus I r e omega times r star plus B y naught of into r star. Okay. For those who are not familiar with taking the square root of I, okay, square root of a complex number, okay, I should note that I power half is equal to 1 by 2 plus 1 plus I by root 2. Okay. Okay, that is the square root of I, okay, because if I take 1 plus I by root 2 the whole square, I will get 1 plus I square plus 2I by 2. Okay. I square is minus 1. So, this 1 and minus and I will cancel out and this will just be equal to I. Okay. So, that is how you can take the square root of and the imaginary number. Okay. So, these are in contrast to what we had for the heat conduction case. This homogeneous part is a complex function. Okay. It is a complex function of R. It is the Bessel function, but it is a complex Bessel function. Okay. And then the total solution is equal to the homogeneous solution okay, plus the particular solution, okay, plus the particular solution. Okay. Okay, plus the particular solution. Okay. And now once I have this, then I can use the boundary conditions to determine the coefficients A naught and Y naught. Okay. The boundary conditions are at R star is equal to 0, okay, partial V by partial R star is equal to 0, okay, and at R star is equal to 1, V is equal to 0. Okay, so those are the boundary conditions. Recall our discussion on the solution, the Bessel solutions, okay, the Bessel functions. Okay. I had plotted for you as a function of r plus j naught of r plus and y naught of r plus. Okay. And that time I had plotted for you it as a function of beta, but the solution will be the same if you plot it in terms of r plus. Okay. Y naught was going to minus infinity, okay, and then it had an oscillatory form. J naught had 0 slope, okay, and then it has an oscillatory form. Okay. And I had also listed for you the points at which this passes through 0. Okay. I had listed for you the points at which this passes through 0. Okay. Since y naught goes to minus infinity, okay, the complex function also goes to minus infinity at r star is equal to 0. The condition on the derivative will be satisfied only if b is equal to 0. So, that the contribution due to y naught is 0. If you have a non-zero contribution due to y naught, that contribution will go to minus infinity at the origin. Okay. So, therefore, you have to set b equal to 0, okay, in this equation in order to satisfy the condition at the axis of the pipe. And in order to satisfy the second condition, okay, I have to find out what is the coefficient A. Okay. That is quite easy to do. Okay. So, I require that 0 is equal to A j naught of root of minus I r e omega, okay, plus I by r e omega, okay, which will give you that A is equal to minus I by r e omega times j naught, the value at r star is equal to minus 1, r star is equal to 1. Okay. That is the value of the coefficient A. V is equal to A times j naught of minus I r e omega times r star plus the particular solution. This will turn out to be equal to I by r e omega into 1 minus j naught of root of okay. That is the solution. Okay. You can see that it is a complicated function, a complicated complex function which contains the Bessel function of a complex argument. Okay. So, now recall that V x plus is equal to V tilde times e power I t, okay, which is I e power I t by r e omega into 1 minus j naught of root of okay. And the solution for Vx is the real part of this. Okay. For Vx star is the real part of this. Okay. So, that is the solution, and obviously you can see that it is quite a complicated solution. Okay. Complex solution with e power I t and a complex function of r, multiply the two, take the real part, and that gives you the actual solution. Okay. And as you can see, it is quite a complicated solution. Okay. So, there are a couple of ways to proceed. First is that you just take the solution and plot it as a function of r for different values of t. Okay. Plot the solution as a function of r for different values of t. Okay. That gives you the numerical solution. Okay. That gives you the numerical solution for the flow in the oscillatory flow in the pipe. Okay. And of course, you can get the numerical velocity profiles and analyze them and so on. Right. But can we get a physical understanding of what is going on? Right. So, this solution itself does not give us a very good physical understanding of the nature of the velocity profiles in the pipe. Okay. First I will give you the numerical solutions of this equation, where I will explicitly plot out the solutions for the velocity field at different points in different phases. Okay. So, for example, we know that as a function of time, okay, the pressure partial p by partial x is equal to okay, it is a cosine function. Okay. Okay. So, at different points in the phase, okay, I can plot what is the actual velocity profile. Okay. Okay, I can plot what is the actual velocity profile and look at what that velocity profile looks like at different points, and then I can try to get a physical understanding. Okay. So, first I will give you a qualitative sketch of the nature of the velocity profiles, and then we will go further and examine the reason why the velocity profiles have the specific form that they do. So, I will continue the discussion of the solution for an oscillatory flow in the next lecture. I will see you then.